Good morning, HVAC team. Today we're going to start chapter 11, which is types of refrigeration systems. Um, the objectives are define refrigeration, list the types or the different types of cooling systems, explain the fundamental principles of evaporative cooling, explain the basic operation of thermoelectric refrigeration, explain the fundamental principles behind the compression refrigeration cycle, discuss the difference between the compression cycle and the absorption cycle. So, operating principles. Most machines that cool or refrigerate something use the same mechanical refrigeration cycle. The cycle depends upon a few basic physical principles. Cold is not a substance or an energy form. It is the lack of heat. Heat travels from hot to cold. That's the second law of thermodynamics. Liquids absorb large amounts of heat when they boil off to a gas. Gases give off large amounts of heat when they condense to a liquid. This is why you want liquid going to your evaporator coil, because the evap coil is where you absorb the heat from the room, and liquids absorb large amounts of heat when they boil off to a gas. So when that liquid changes state into a gas, at that point is when it absorbs the most heat. And then the same thing on the flip side is you reject more heat. Gases give off large amounts of heat when they condense to a liquid, which is why we want vapor going to our condenser, because the condenser is where we remove the heat. So like they said, cold isn't a substance that we're providing, that we're pushing out through the vents. It's the lack of heat, which is making that air cold. The same air that's getting sucked out of the room through the intake duct or the return duct, that same air is being blown right back out through the supply ducts. But the only difference is before it comes out of the supply, all the heat is absorbed from it, because the liquid that's in that evap coil boils and absorbs the heat from all the air that's going across that coil. And then that same vapor that was just liquid a moment ago, it evaporated into a vapor, absorbed all the heat from the air. That same vapor with all that absorbed heat energy is shot straight out to the compressor, and then from the compressor into the evap or condenser coil, and then that's when it condenses to a liquid and releases the heat. So all the heat we just absorbed from the air inside the room in the condenser is now being rejected all the heat that was absorbed from the air in the room at the evaporator is now being rejected at the condenser. So refrigeration machines do not pump cold in, they pump heat out. The problem is that heat only wants to travel from hot to cold, and when you need your air conditioner, it's usually hotter outside than inside. So the challenge is to pump heat from inside, where it is relatively cool, to outside, where it is relatively hot. Operating principles. When something is boiling or condensing, its temperature remains the same. The temperature at which a liquid boils is controlled by its pressure. Relationships. If the refrigerant is a high pressure, it is also a high temperature. If it is a low pressure, it is also a low temperature. So temperature goes up, pressure goes up, temperature goes down, pressure goes down. That's the relationship that pressure and temperature have. Gas always has relatively high heat content, and liquid always has relatively low heat content. Refrigerant will be found in the system in one of three conditions: superheated, saturated, or subcooled. Each of the four main components has an opposite. The compressor and the expansion device are opposites. The condenser and the evaporator are opposites. Heat is added to the refrigerant in the evaporator, and then it's removed at the condenser like we just talked about. The the condenser and the evap are opposites because of that. One is absorbing heat, one is rejecting heat. One is being pumped full of liquid, no, not full of liquid, but one has liquid entering and then vapor exiting, and then the condenser has vapor entering and liquid exiting. And then compressor and the expansion device, those are also opposites because they both are the 2 points in the system where a pressure change takes place. At the compressor, that's where the pressure is increased. At the metering device, that is where the pressure is decreased. So they separate the high and the low sides of the system. So from the compressor to the metering device is all high side. And then from the outlet of the metering device back to the inlet of the compressor is the low side of the system. So when you hear high and low sides, that's what they're referring to. Everything after the compressor is all high pressure. It doesn't go back to low pressure until after the metering device. The compressor adds a sizable quantity of heat to the refrigerant. The heat added in the evaporator and by the compressor is removed in the condenser. The heat balance of the overall system is shown in the following formula. Heat added in the evaporator plus heat of compression equals heat rejected in the condenser. Absorption refrigeration systems use heat and the process of absorption to move the refrigerant instead of a compressor. The absorption process takes advantage of the fact that some chemicals have an affinity to other chemicals. Absorption cycle. Under a high pressure, the ammonia refrigerant condenses from a gas to a liquid in the condenser, giving up its latent heat in the process. The high pressure liquid now passes through a refrigerant restrictor where its pressure and temperature are reduced, which is your metering device. The transfer of heat is essentially the same in the absorption system as in the traditional mechanical compression cycle. Heat is absorbed in the evaporator and rejected in the condenser. Absorption cycle. A second fluid that has an affinity for the refrigerant absorbs the refrigerant in the absorber. This has the effect of sucking the refrigerant out of the evaporator and creating a low refrigerant pressure in the evaporator. The absorption process replaces the suction stroke of the compressor. When the vapor refrigerant is absorbed into the solution, it condenses back into a liquid. This gives off a great deal of heat, normally called the heat of absorption. If the heat of absorption is not removed from the solution, the absorption process will stop. Let's get rid of that. Regenerator. The absorbing solution can only absorb a limited amount of refrigerant, so the water ammonia solution needs to be regenerated for the system to keep operating. In the case of water and ammonia, water will absorb about half its weight in ammonia. End of absorption cycle. The generator separates the refrigerant and the absorbent by boiling the refrigerant out of the absorbent. The solution cycle is now complete. This creates a high pressure on the high side of the system. The refrigerant vapor is sent on its way toward the condenser, and the weak solution is sent through a restrictor back to the solution cooled absorber. In addition to the components mentioned, there are a number of other components added to the system for increased efficiency. Evaporative cooling systems. Evaporative cooling reduces the air temperature by evaporating water. Air that has been cooled through direct evaporative cooling still has the same amount of heat, but its temperature is lower and its humidity is higher. Evaporative coolers can drop the air temperature by as much as 20 degrees Fahrenheit if the entering air is dry. Pump, sump, and media. The pump pumps the water from the sump at the bottom to the top of the media where it runs down the media. The blower moves outside air across the media and into the house. Water evaporates from the wetted media, reducing the temperature of the air. A float controls the water level in the sump by allowing makeup water to fill the sump when the water level drops. So what they're talking about in simple terms that you've probably heard is a swamp cooler. Evaporative coolers are swamp coolers. And the media that they're talking about is a lot of times it's this hay looking stuff, or sometimes they have this honeycomb looking like material that's all along the sides. So I'm sure many of you seen these swamp coolers on the sides or at the tops of buildings. So it's just a big metal box with vents on all four sides. And right behind those vents, you have your pads or your media. The sump is just a tank of water on the bottom, and the water gets pumped to the top like a sprinkler, and it just sprays down, or it just kind of runs down and cascades down the media. And as that happens, it just continues. It cascades down back into the sump, and then into the pump, and then comes right back up, and then cascades down. And it's just a complete continuous loop of water. And then there's a big blower motor sitting right in the middle of this entire thing. So you just got this big metal box, this media on all four sides, these pads or whatever you want to call them on all four sides. And all they do is allow water to evenly kind of cascade down them with this big blower motor in the middle. As it's turning, it's sucking the air through the sides of the swamp cooler. So all the outside air is coming across the wetted media. And then so by that air coming across there, the water starts to evaporate and it loses heat. And when that happens, the air going into the building is then cooler than the air that was coming in. Then the entering air coming into the media is going to be cooled by evaporation. And then once it passes through the media, it goes down into the building. Yes, cooler, humidified air. That is not the most effective way of cooling a place. I mean, it's useful in places where there's really, really high or really dry places, rather. Not a lot of humidity at all. You need to add some humidity to that air. Desert areas and places like that. But they don't cool as much as a refrigeration system. So there's no refrigeration involved with evaporative cooling. It's just simply the water running down the wetted media with the blower motor turning in the middle. And then as far as the pump they're talking about, the sump has water in it. There's a float, not the pump, but the float. There's a float switch. And if the water level drops, kind of like that float in the back in the toilet tank. Once that thing drops, it's going to open up the valve and allow more water to come in, and then it'll fill back up, and then it'll close the valve again. And once it drops, it'll open the valve again. And the reason why you lose water is because evaporation. So over time, the level in that sump will start to drop. And when that happens, it'll open the valve automatically and allow fresh water to come in. So that's what the evaporative cooling is. Direct evaporative cooling. Evaporative coolers are constantly replacing the air in the house with air from outside that has been cooled by evaporation. This type of evaporative cooling is called direct evaporative cooling because the water is directly exposed to the air entering the building. For this system to operate correctly, air in the house must be allowed to escape. This is normally done by opening the windows. Product air. The product air will be delivered into the house. The working air will be expelled to the outside. kind of like the supply and return. Product air is always separate from the working air so that the air entering the house does not pick up moisture. Cooler temperatures. Air that is cooled by the first set of plates is used to cool the next set of plates. This process occurs multiple times in a short physical space within the exchanger, resulting in progressively cooler product and working air temperatures. Practicality. Thermoelectric cooling does provide a small, lightweight cooling system for areas that would be difficult to cool with a traditional refrigeration system. Thermoelectric cooling does provide a small, lightweight cooling system for areas that would be difficult to cool with a traditional refrigeration system. Okay, all right, both points were the same. Moving on. Uses. Thermoelectric cooling has been applied to electronic systems, spaceships, and picnic coolers. So just small spaces. So in summary, the purpose of a refrigeration system is to move heat from where it is not wanted to where it is unobjectionable, or where it doesn't matter. There are several kinds of cooling systems, including absorption, evaporative, thermoelectric, and mechanical compression. Other cooling mechanisms include evaporative coolers, which cool the air by evaporating water, the absorption cycle, which uses heat and an absorbent fluid to create the needed system pressure difference, and thermoelectric cooling, which transfers heat using electric current and the Peltier effect. So that is all for chapter 11. Hope that was helpful. Any deeper info will be in your book in chapter 11. Flexi Quiz has been updated, so feel free to get a head start on your classwork and homework. And outside of that, I hope everybody's being safe and being healthy and staying motivated. Stay in your books. This will be over soon, so we'll be back in class, and don't want to get back to class and have people feel like they got to start then because they didn't do anything now. So please, please, please study, read your book, and stay caught up on Flexi Quiz. And I will see you on the next one.